All right. Here we have worksheet 10. Looks like we got the old iPad system working here. And I'm giving you guys the equations for just a few of the main ones here. So we have this double and single slit equations, right? So, with double and single, we can see that they switch relative to the max and min, right, between single and double. For instance, the max bright is the equation you would use for the minimum dark of double and single, respectively, right? So just kind of remember that you only need to know two, but you need to switch them. That m value is the order number. So, like on the other end of a double slit experiment right here, or in this case, single, right? It goes like the wave goes like that. So each order number will represent one of these either peaks or troughs there. Okay. And then wavelength in a non-air substance, this really comes into play with these thin film interference where you have this like light coming in, like goes through air, then it hits oil, then it hits water. You need to find that lambda of the substance, where lambda of the substance equals lambda air over n of the substance. And the way he gave you guys the equation, you already incorporate you already incorporate this equation into these guys by having n on this side of the equal sign, whichever way you want. I just do it this way. To me, it makes more sense. And then I think it's important to recognize if I'm recording, right? Yeah, okay. I think it's important to recognize like what is destructive. It's basically when these two waves are destructively interfering. So imagine two opposite waves. So when you add them on top of each other, they cancel out, right? And then constructive is like when they're of the exact shape. So when you add them together, it ends up being something like louder, right? And something I like to think about is like with sound. So when you're equidistant from two different speakers that are both emitting sound, the sound amplifies. That's why, like at a concert, like there's the speakers on both sides and super loud. And then differently with like noise canceling headphones, something like this, when it hears a sound, like right now at my apartment, my roommate is making a bunch of noise. I'm trying to focus. That noise gets interpreted by the headphone and it emits a frequency that's opposite to that my roommate's making, and it ends up canceling it out. And that's how you make that's that destructive interference kind of cancels out. And it has to do with like the phase shift, right? So we'll talk about that more in a sec here. Uh, I do want to mention though, when we have a phase shift, um, we'll have a like the light in these thin film type questions. I think numbers 3 and 5 maybe. It's when it goes from the index of refraction from low to high. At that point, there's a phase shift, and that's how you know you switch the equations, right? So with one phase shift and constructive interference, you'll use this equation. If there's two phase shifts on the next phase shift, you have to use this equation. Like it goes back and forth, back and forth, starting with this as one phase shift. For constructive, you start with one. And most of the time, these thin film start you using constructive. So, like you're having a thin film question, there's one phase shift, use this equation to solve. If there's two, you have to use this equation, and then you'll switch to this one at the second one. So you have to kind of remember like you're in a cycle between them. Okay, so in Q1 here, we are told that we have two narrow slits. There's some distance between them. They're illuminated by a monochromatic light wavelength of that wavelength. Determine the angular position of the first maximum. And then if we placed a plate that 1.5 meters away, we want to determine the distance on the film where the central maximum would be. And yes, we're solving for x using that tan theta x over L equation. Okay. So what kind of experiment is this? This is, sorry, whenever I'm on the iPad, I need to zoom in, otherwise my handwriting gets really bad. It's a double slit experiment. Let me just write one. Sorry. Oh my goodness. All right, gotta pause. iPad's not working. All right, sorry about that. At any moment, this recording will stop out of my control. Okay, so here we have a double slit experiment here, and we're gonna figure out which equation we're gonna use, right? So what are we looking for? For that first position maximum, right? So it's gonna be a max bright. So double slit max bright, what's our equation? D sine theta, which is equal to, m lambda here. What are we solving for? It's that angular position, so theta, which is going to be equal to the sine inverse of that order, which in this case is going to be 1 lambda over d. All that stuff's given. You solve for theta, it's going to be equal to 0.2556 degrees. Okay, so that's what's it called? Part like 1 here. And then part 2, pretty easy. Also, we're going to use that theta to solve for x, which is going to be the distance on the film between that central maximum and then that first order. So that first order maximum, right? So it's like from where it hits to that first peak. So tan theta is equal to x over L. We're going to solve for x. So x is going to be equal to L tan theta. X comes out to be equal to 0.006 centimeters. Okay. So Q1 is pretty quick, and kind of same with question 2 here. Just kind of introduce us to this concept here. So again, a light is incident on 2 narrow slits, therefore double slit. And they're set for each slit distance. That d value is 0.13 millimeters, and the angular separation between the central peak and the second maximum is 0.3. We're solving for lambda. Okay, so again, which equation are we going to use? D sine theta. It's double max, so max bright. So that's the equation we're going to use. We're solving for lambda, so lambda equals d sine theta over m. Everything's given. Here we're plugging in m as 2. Lambda is going to come out to be 340 nanometers. I mean, there's a lot of confusion on like which m you plug in. It's normally it's going to be the one that give you, right, second maximum. And in that case, we're plugging in 2 for these double slit bright types. And the reason we need to use that second one is because we're given that angular separation between, it's not the first, it's not the first one, it's the second one, right? So that angular separation we're getting, theta, is in relation to m equals 2. So we need to make sure we use m equals 2 when we're solving for lambda. If you use like 1, for instance, it'd be underrepresented. Okay. Q3. So this is where it kind of kicks up. So here we have a thin film of alcohol. Okay, so this is a thin film type question, right? You just read that and see. And we're going to see that we have the system where it's like n equals 1, n equals 1.36. That's that thin film of alcohol. And then below that alcohol is a glass plate, which is n equals 1.51. So imagine like how things are going here. It's going to be something like this. So identify our phase shifts. When do a phase shift happen? It's when our n goes from a smaller value to a lower one. So, 1 is smaller than 1.36. So there's a phase shift here. 1.36 is smaller than 1.51. So there's a phase shift here. Sorry, bad drawing. Wow, that was perfect. That was a free hand. It was right on the money. And kind of how's the light behaving here? It's going to go like this, like that. Here's our thin film of alcohol right here. So I'm going to write ALC for alcohol. We're told lambda max and we're told lambda min. So now we know we have these light and dark equations. And I'm going to rewrite the equations, so 2t equals m max, lambda max. So here we're using that max setup. This is our first one. And I'm just going to divide it by n equals 1 right off the bat, just because I'm going to want to consider what it is in that substance, right? Because we know what the lambda, they give us the lambda through air, but we need to consider what it is through that alcohol substance. Okay. Then we also have the equation 2t equals m min. Remember, so phase change, we switch the equations we're using. Lambda min, and divided by n1 again for the same reason. So I guess I don't even know if I read the question here. So you have a thin film of alcohol. It's on top of a glass plate. So light comes in, and the wavelength, the wavelength change is incident on the thin film. The reflected light has a maximum when lambda equals 756 and a minimum when it equals 432. We want to just determine the minimum thickness of the film. Okay, so how can we find the thickness of the film? It's embedded in this T, right? In this T. We have 2 equations, but we also have other unknowns, right? So this is known, this is known. This is known, this is known, but this is also unknown. So I have these two equations with two unknowns. I need to be able to manipulate them such that I can plug in something to find the other thing. So how I'm going to want to do that is recognize that they're both equal to 2t, right? So because they're both equal to 2t, I can set these equations equal to each other. And setting these equations equal to each other, I'll see that m max lambda max divided by n1 is going to be equal to m min plus 1/2 lambda min. Okay. Again, over n equals 1. You can cancel those guys out. No. So it's convenient that it worked out that way. And I want to get the lambda max on one side. I mean, the lambdas on one side, and then these order values on the other side. Because that's known, that's unknown. Okay. At this point, I'm going to want to multiply. It's easier for me to get rid of this fraction here. So I'm going to multiply everything by 2 here. So I'm going to have 2 m min plus 1 over 2 m max. Okay. And if you do the ratio right here, we'll see that these units cancel out. We can treat it as a ratio where this ratio is going to equal to 7 over 4. Okay. And if you have a good eye, you'll be able to solve for m min and m max right off the bat. Because what can you plug in up here to get 7 on the top, right? You plug in a 3. 2 times 3 equals 6 plus 1 equals 7. So let's say m min equals 3. M max is going to be equal to, what can you plug into the bottom down here to get 4? 2. So 2. All right. And now you have these two values. You can plug in either one of these into any one of these equations up here and solve for t. I'm just going to choose the one with max just because it's easier. So I'm going to take that this 2 right here, plug it in up here. I'm going to say 2t. It's going to be equal to m max lambda max divided by n1. I'm going to get t alone. So it's going to be m max lambda max over 2 n1. Plug everything in, work everything out. T is going to be a very small number. So equal to 0.0000. So that's 3 and 3 zeros here. 5, 5, 6 nanometers. I'm sorry, meters. I guess I could have converted that to nanometers, so it made it a lot prettier, but I still think it's fine. Okay, so that's thin film. Let's keep it going here. Okay, number 4. So this is I think there were, oh no, they tell us actually. So we have a light with a wavelength of 400 nanometers. It passes through a single slit. It creates a central peak that is 4.8 centimeters wide on a screen that is 2.3 meters from the single slit. We want to determine the width of the slit. So what's the, what are we solving for here? Solving for D. So Q4. What kind of equation is this? Single slit. So let's draw the diagram. Something like this. It's going to be like, apologies. It's not great. From here to here is that D. That's what we're looking for. From here to here, let's call it X. Call this Y. Call this Y prime, where Y prime plus Y prime equals Y. We know that the, it goes 0, then M1 is the first dip right here. Excuse me, I want to sneeze. Oh wait, now it's awkward because all right, I'm not going to sneeze. See, that was a trick. I knew if I said I was going to sneeze, I wouldn't end up sneezing. So I said I'm not going to sneeze, and that tricked my body into sneezing. Anyway. All right, and that's theta, right? Okay, so we're going to need to work for a few things. The first thing we're going to find is that angle theta, because we know that we're dealing with a the single slit scenario, right? And we're looking for the dark spot, I believe. Or maybe, yeah. Okay. So how can we find that angle theta? Well, the first thing we're going to do is use that y prime and use that. So tan theta equals y prime divided by x. And what do we have? We have y. We don't have anything about y prime, but we know that y is equal to 2y prime. Therefore, we can say y prime is equal to y over 2. We can incorporate this again, y equals 2x. We can now rearrange this equation to solve for theta. So just bring that tan inverse into here. Substitute everything in, solve everything out. Theta comes out to be 0.06. I'm sorry, 0.6 degrees. All right, we have an angle. Now, which equation? D sine theta equals m lambda. We want to solve for d, get d on one side. Plug everything in. What are we plugging in for m here? It's going to be 1. We're looking for that. What do we see? Oh, well, we're just going to use the first one, but I guess you could have used other ones, but then you would have had to like adjust your y value plugged in up here. It's easiest to use m equals 1, so because that's the theta we solve for. It's going to be 1, and then plug everything else in. This guy comes out to be 0.000382 meters. All right. Cool. Now, number 5, I think this is a good one. You know, it's kind of a shorter worksheet here. It goes pretty fast. Q5, we'll see that we have another thin film question. So we have a wedge below with length L. It's formed between two glass plates, and they give us the index of refraction. They're separated on one edge by a small block. The interior of the wedge is filled with a material whose index of refraction is n equals 1.15. The light is normally incident on the wedge from above. At what x value is the first bright band for red light of wavelength 600 nanometers? Okay, so this one's kind of a, they gave us a lot of information. Let's draw this out nice. Watch this. Rotate this. Oh, uh-oh. Oh yeah, I thought I used to. Oh yeah, there we go. All right, we can get it. Perfect. Okay, so we have this situation where n equals 1.45, n equals 1.45, and here n equals 1.15. Okay, we have light coming in, it's going like this, comes in, it's here, goes here, something like this, like this. Okay. And we know there's one phase shift. Where is it? It's over here, low to high from right here. We know the distance between them is h, and what was h equal to? That point, oh yeah, they give us h, 0.035 millimeters, right? And we'll call this L. And we're solving for this x, where that first bright band is going to be. Okay, so, you know, it's constructive. We're using the first one. So which equation? 2, I'm going to use D. I'm going to use T, actually. I want to be consistent. 2T equals m plus 1/2 lambda of the substance. You know, where lambda of the substance equals in the lambda of the in air divided by n of the substance. So make sure you make that adjustment when you're calculating. We're going to solve for T, which is going to be equal to the first one for constructive is 0, so plug in 0 here, times lambda of the substance, which is 690 times. That's like with the adjustment, that being this adjustment. And then 2 times 1.15. Okay, because we brought that to the other side. T comes out to be equal to 1.304 times 10 to the minus 7 meters. All right. That's not what we're looking for, though. What we have found, you know, is T. But we can use that T now to solve for X because we know that the ratio of T to X is going to be equal to that of H to L, right? It's like two triangles within each other. So we can do a rearrangement here and see X is equal to T L over H, where we know T, we just solve for it. L and H are given. X comes out to be equal to 3.19 times 10 to the minus 4 meters. All right. Oh, nice. Cool. So that's the main part of the worksheet. I included some extra practice on this just because I think just like high volume of these types of questions is helpful. So that's going to be extra practice questions 1 through 4 here. If you want the solutions for that, just email me and I'll email you back a PDF with the like my handwritten solution for them. Let's see. The only thing I want to bring up is, for instance, on the question number 2, we can see that the fringe pattern, or just like in general, right? So for these single slit scenarios, the fringe pattern is formed by like these alternating bright and dark, like fringes, right? So it'd be something like this, where this is dark, this is bright, and this is dark. And like the first M value you would use is 0, and this would be 1, and like this is -1, right? So you have to remember it's like alternating in that scenario. Okay, anyway, that was a little tip if you wanted to do number 2. So if you want to see the answers to those, just email me and I'll email you back. All right, cool. Now, how can I, oh,